this one.
Word.
Word. Then we will go to PowerPoint. First Word.
This one.
This one. So in my article, I noted down 4 printing errors, which I will quickly go through. This slide tells, out of that most important is the stress diagram, where you find in the read, I have taken the line from 890 plus 540, from there the lines to start. The printing has started from 540. So that is a major error in this printing. Rest are all minor issues. There were only 4 printing errors were there on that. So now, because of the shortage of time, I am not going through except this. Now I will go back to this a PowerPoint presentation. A PowerPoint presentation. Okay. Okay. This is a slideshow starting is there, no? You put the slideshow starting, put slideshow, and from the beginning. Okay. Now I will start my PowerPoint presentation, analysis of partially pre-stressed beams. First is, what are the references I have relied upon? PCI Design Handbook, I will try to show this also at the end. PCI Design Handbook 7th edition, Analysis of Cracked Pre-stressed Concrete Section, a Practical Approach by Robert E. Mast, PCI Journal, August 1998. Steel Stresses in Partially Pre-stressed Concrete Members, Walter Dilger and K.M. Suri, PCI Journal, June 1986. Incidentally, if you see the PCI handbook earlier editions, they write this area is not researched much, it is under research, it will take time to come up with a recommendation. You will find PCI handbook 1, 2, 3, 4, it is like that. Only 5, 6, 7 onwards, it is, you have given the procedure, but the main man who is to be appreciated is Robert Mast. So if you happen to see any paper on Robert Mast, please go through. He is a practical engineer and he gives you all practical solutions. After his approach only that he took it to PCI handbook and they developed the message for this crack section analysis. Now, what is a fully pre-stressed member? A pre-stressed member fully in compression or having tensile stresses less than or equal to allowable under loads and pre-stress is called fully pre-stressed. What is partially pre-stressed? A pre-stressed member having tensile stress greater than the allowable tensile stress leading to cracking under loads and pre-stress. Now, if you see the diagram, first diagram is dead load and pre-stress in fully in compression. Below that, dead load at pre-stress and live load is in fully again in compression but reduced compression. Now, the third page is third photograph line, you will find section in compression but stresses becoming 0. This is what, as per the Eurocode and other codes, generally people take it as a fully compressed section. The fourth diagram is FCTK 0.05. This is also, American code also says some Eurocode are silent but gives an indirect method that it can be taken as a fully pre-stressed section where the tensile stresses are within limits. Now the last stage, that is partially pre-stressed section, where you will find the tensile stresses are exceeded the limit, that 0.05 value is somewhere else, so the section has cracked. Now, analysis of partially pre-stressed member, Robert F. Mast says, to fully understand the behavior of a pre-stressed concrete member, cracked at service load, an analysis of the cracked pre-stressed section should be made. This analysis is needed in order to find the change in steel stress after cracking and for finding the appropriate flexural stiffness used in the deflection calculation. The analysis of cracked pre-stressed section concrete requires at best the solution of a cubical equation. The complexity of solution requiring the use of charts, tables or special software has impeded the use of pre-stressed concrete members with the tensile stresses beyond the codal limits for nominal tensile stresses. This is at the beginning. Nowadays computer program, you can develop it and you can make this into a computer program. The purpose of this paper is to present analysis method using conventional section properties software. The solution requires iteration. This is very important. This partially pre-stressed beams always requires iteration. It cannot be done without iteration because the neutral axis will keep on changing. But the bulk of the work is done by existing section properties program. The iteration may be done manually or small additional program may be written that will do the iteration using an existing section property program to do the computation inside an iteration loop. The iterative procedure consists of assuming what is the procedure? Assuming a depth of a neutral axis, computing section properties of the net cracked section, checking the stress at the assumed neutral axis location, and revising the C as necessary to make the concrete stress equal to 0 as the assumed neutral axis. Though the code speaks about the crack section properties, decompression, crack width, deflection and fatigue, all has been given in the code. There is no definite procedure mentioned in the code to analyze the partially pre-stressed beam under service load for the above parameters. Moreover, code cannot give these procedures. Now, Chris Sandy, another very important man for Eurocode purposes, if in checking the decompression, the extreme fiber is found to be cracked, the check of the decompression at specified distance from the tendons becomes iterative. Because as per the code, from the cable 100 millimeter, only your neutral axis has to come. The neutral axis is prefixed. It cannot come closer to than 100, or it can be more than 100, but it cannot come closer to 100. So to locate this neutral axis, you have to keep on iterating. So that is why both the authors says a partially pre-stressed becomes an iteration process and it is not a direct process. What are the checks to be performed? Check for stresses, both concrete and steel, crack width, deflection and fatigue check. First what you have to do is, first check the section using Gross properties and verify whether tensile stresses are greater than the allowable tensile stress leading to cracking. If so, then proceed with the crack section analysis. First make sure the section cracks. Then if you see my paper from there I have proved the section has cracked. That tensile stresses is 419 is much greater than 330, so it has cracked. Now, complication, what are the complications? Part of the load is applied on precast section, part of the load is applied on composite section, cracking of section happens under the live load and complete change in the property takes place. To tackle this problem, bare beam approach as suggested by MOST and PCI will be followed. The article gives this procedure. Estimate the net, now proceed step 1. Estimate the net pre-stressing force after all losses. Apply the self weight of beam, deck slab and net pre-stressing force and estimate the stress on the bare beam. Paper example, P is 347 tons, moment is 124.4 tons, bottom fiber stress is 803, top fiber stress is 580. Assume fictitious deck slab. Now the deck slab is not there, but assume it fictitiously and estimate the stress at top of slab 540 ton per meter square. Calculate the fictitious force in the slab. Apply on the composite section this fictitious force, the net pre-stressing force and applied on the bare beam. The stress will be the same as obtained in steps 2. Stress 2, what you are analyzing, that you will get the same stress if you include the decompressive force and then take it as composite section. That's what it means. In the bare beam, you apply the pre-stressing force and the moment what it has been applied on the bare beam. Now you calculate the fictitious force, take it on the composite seam, the fictitious force, moment, pre-stressing force and applied. Both of them will give exactly the same results. This is check number 1. Your value has to match, otherwise you have gone wrong. Calculate the CG of forces, fictitious force in the slab, pre-stressing force including decompression force in untensioned steel due to loss of decompression. The decompression force is the force in pre-stressing steel when the stress in concrete around the cable is 0. This is also given in 112. PCI recommends add back the elastic shortening block force to the effective pre-stress to get the decompression force. MOST recommends effective pre-stress can be used as, he gives one simple reason that you forget about all these things, whatever the effective force remains, you take it as decompression force. That will lead to a sort of conservative approach. This is not going to be, you have more crack width, you may have more stresses. But this is a very conservative approach. You can follow it, but if one is interested to calculate the decompressive force, they can do it. In this example, the total force is 359 tons. The fictitious force is, that is 347 plus 12, if I remember correct, 347 is the pre-stressing force, 12 tons is the decompression force, 249 is the fictitious force on the slab, 19 tons force is in the, 22 tons is the force in the normal steel, minus 3 tons is the decompression. So 19 tons is the force in the non-pre-stressed steel. So the total force acting on the section is 589 tons, acting at 0.726 meter from the top of the section. Apply the above forces in total moment on composite section. The composite section will turn out to be a cracked section. Assume neutral axis, determine the area of cross section, MI of cracked section. Calculate the stress at the neutral axis, it should be 0. This is another check. The bare beam and the composite beam will give the same stress, check number 1. Check number 2, your neutral axis has to be, give the stresses is 0. Now in this problem, if you see P by A is 1919 and the net movement is 89 ton meter, and you get the net stress as 919. So the net stress is due to bending is 919, axial stress is 919. So the net stress is 0. That means your neutral axis, what you assumed is correct. If this is not 0, you have to either below or you have to add, you have to shift. Where to add, where to take it up, where to take it down, I have written in my article. Now, estimate the stress in top of slab, bottom of slab at various locations of the beam up to neutral axis in pre-stressing steel. The fictitious stresses have to be subtracted from the deck slab and bottom to get actual stress in sleeve. Calculate the total compressive force and tensile stress force, keeping in mind the changes in the stress in steel has to be added to the existing stress in level to get the total stress. The force and the moment equilibrium has to be started. Now the third and fourth check.
Mr.
The force
Vishwanathan,
equilibrium.
please, can you wind up now? How much more?
Maybe another 2-3 minutes.
Okay, right.
So I'm sorry, I will just run through now to be for your benefit. I have seen first the bare beam approach is giving 540, 58, 440 in the deck slab, and the composite beam also you have got that bare beam approach. When I put that fictitious layer also, I get same 580, 540. Then if you see the net pre-stressing force is 37, 312, total force is 359, and 22 tons is untensioned steel, decompression force is 3 tons, net compressive force is 19 tons, fictitious force in the deck slab is 249 tons. Now I have given the forces on the section, and cracked moment of inertia I have calculated the neutral for the neutral axis, and I proved the stresses in the neutral axis is 0. Then I have seen the total tensile force is 387 tons and total compressive force is also 387 tons. So the tensile stress is equivalent to the compressive force. The section is in equilibrium. Then the moment due to this is 393.4 tons and moment is 394 tons is external moment. So you will find that bare beam, it gives you the same stress. The stress in the neutral axis is 0. The equilibrium of force is obtained. The equilibrium of moment is obtained. That means you are right in your approach. Now stresses are within the limits. When I did the check, the stresses are within the limit. The steel stress I have found out. Then the crack width regulations I had gone and checked. Then finally I have gone to the deflection. I will tell you this Astro principle you can do 2 methods, bilinear and effective moment of inertia. So I have done these things in the paper, and I have proved all 3 methods I have taken and proved the deflections are almost same. You can use any one of 2 procedures gave similar results. So I have stuck to that and then said that 2 procedures can be followed. Now fatigue verification, which has not come in IRC so far, the method is you have already calculated the fluctuating stresses in the pre-stressing steel. Take it to SN curve and then check whether your fluctuation of stresses are within the limits or not. Now summary of crack section analysis, I will leave it, and this is the last 1, 2, 3, 4. I have summarized what is to be done for service to limit states. I just due to shortage of time I cannot help much, and whatever I have written in my paper you can go through, and PCA handbook 7th edition if you go through you will be more clear. Thank you.
Thank you, Mr. Vishwanathan. I'm sure it will be of great value to all designers, bridge designers, what you have said right now. I have another proposal to make. I have 6 papers to be completed in this session. Since we started late, we don't have time. So I'm proposing that we skip the tea break in between because you've already had tea just now, just a little while ago. So we'll skip the tea break and continue with the presentations. Thank you.
Thank you.
The next presentation is paper number 647, Effects of Modulus of Subgrade Reaction on Thickness of Rigid Pavement. A case study by Sri S. Singh, Dr. G.D. Ran Singh Chung, Sri R.N. Sri S.N. Sachdeva, Dr. Praveen Kumar, and Dr. M. Parida. The slot given here is 15 minutes, but I think you'll have to make it much shorter because if we have to cover all of the papers.
This paper is co-authored by 4 people, and I am introducing Dr. Praveen Aaron. Dr. Praveen Aaron is professor and group coordinator of Transportation Engineering Group at IIT Roorkee. He is a recipient of many awards, including prestigious Jawaharlal Nehru Award of IRC and 3 times Best Teacher Award at IIT Roorkee. So I invite Dr. Praveen Aaron.
Thank you. We have a very little time with us because Chairman is saying that we have to complete in about 12 minutes. We have 3 other authors with me. We have Professor Manoranjan Parida, Dr. Ran Singh Chung, and our research scholar, Mr. Suren Singh, a young researcher from Haryana. And this paper is basically a research work which came to our mind when we were doing a consultancy project. We were asked to design a toll booth road in Agra, and it was a normal routine process of designing of any road for the rigid payments. Though I am not very much known for rigid payments, mainly I am known for PMJSY, with which I am linked from the very first day when PMJSY was being conceived. So this road was given to us for the design, and with that part, we started working on this project, and where is the okay, okay. Okay. So this work was being awarded to us to design this Agra toll booth road. And in the process of designing, we came to know that when we were going to design it, we found that the result was coming same as we were. Okay. So we were trying to do the design, and we were seeing that after changing different parameters, the result was coming to be the same. There was no variation in the result. So in this paper, we have divided into different parts like introduction, then background and methodology, comparison between IRC 58 and Portland Cement Association work, then comparison between IRC 58 2015 and IRC 58 2012, then laboratory casting of slab and FEM analysis, finite element analysis, and then the conclusions. So as we know that key factor in the design of any structure is the economy, especially when we are doing the design for the rigid payments, it is not the direct design. We assume some thickness, we try to find out the stresses, and then we find out whether it is working well or not. But at the same time, we try to find out the minimum thickness of the slab so that it is done with the minimum cost. So by proper designing of the payment, the total cost can be reduced, and various factors which affect the design of rigid payments are, because many of you who are sitting there may be from the bridge background, they may be knowing about the concrete design, but many of you are from the flexible payment design background, so they may not be knowing how the rigid payments are being designed in the country. So the factors which are affecting are subgrade strength, subbase type and its thickness, and shoulders conditions also, because if you have good shoulders, they can provide the strength to the pavement also. And based on that, we have the pavement quality concrete thickness. And even if we are able to reduce 1 centimeter thickness of the pavement, it can reduce the cost enormously. But at the same time, many people are doing it without design also, like in Uttar Pradesh, I remember 2-3 years back, there was one yojana by Uttar Pradesh government, and they announced that there will be thicknesses of the rigid pavement will be 10 centimeter only, which was bound to fail. And during the training courses which we organize in Roorkee many times, many of you who are coming from Uttar Pradesh, you know that we told them that these roads are going to be filled, because 10 centimeter thickness will not solve the purpose if the tractors and the big buses are coming over the road, even if it is a PMJSY road or Ambedkar Yojana road, tractors are bound to come on the rural roads. So we have to see both the sides. It should not be so less that the road is failing, but at the same time, it should not be very high so that the cost is very high. And the The earliest approaches for the design of cement concrete pavements were based on Westergaard analysis, like the different approaches were ASTO method, Ostrod method, PCA method, and then we have IRC 58, 2011 and 2015. These are for the main roads. For the rural roads, we don't design with IRC 58, where we are not providing the dowel bars also. And in this, the effective modulus of subgrade reaction is the most important factor. As we know that in the design, normally we don't have the K value, which is to be found by the plate load test, but what we do is we find out using the CBR method, and then we compare, or we have the correlation between CBR and the K value, and we try to find out the K value. Because K value is the most important factor in the design of rigid pavements, while for the flexible pavements, we are designing with the CBR value. And various other works were done like Meshram, etc. They used our finite element 3D analysis for this purpose. And we have, as I said, we started the work for Agra Ring Road.